Well, that was creepy. Got it. So we're going to start off with kind of uranium lead basics this morning. And, for a lot of you, this is going to be review. Just sit back, relax, enjoy the show. And then later this afternoon, we'll kind of get into more complex stuff as we go. And Kurt will be working a lot with the hands-on components. How do you reduce your data? How do you display your data? How do you think about it critically? So getting started, we're going to start off with these decay chains. So uranium lead is a radioactive decay chain, right? We have a parent isotope, in this case, uranium-238. It works its way down this decay chain all the way to lead-206. So this is our parent and this is our daughter. And this is actually a relatively simple decay chain, which is great for uranium lead geochronology. There's no significant branching, and all of the uranium goes to lead. The half-life of this reaction is actually quite long, so 4.5 billion years. That number should sound familiar to most geologists, right? Age of the Earth. So we've only gone through one half-life for this system. And the other thing to point out here, two things. One is that this is the rate controlling decay, that very first decay. And then the other thing is this guy here, thorium-230. Turns out he's also radioactive and decays to lead-206. This is a bit complicated, right? Because if you have lots of thorium-230 in your system, you could actually get extra lead-206 down the line. Turns out this isn't a huge problem for zircon, but something to keep in mind. Yeah. Okay, second decay chain, uranium-235 to lead-207. This guy works the same way. We start up here, uranium-235 comes down the decay chain, ends up at lead-207. Similarly, we have this guy here, protactinium-231. We have lots of protactinium. We can get extra lead-207. The half-life, wildly different, only 704 million years. So this is the power of uranium lead geochronology. We have two clocks, they're ticking at different rates, and we can combine those to get a really meaningful age, and we can test how good that age is by comparing our two clocks. I know better than to do that. No. All right. You would think that after an hour we would have gotten through the technical difficulties, but here we are. Okay, third decay chain, thorium-232 to lead-208. This is not super important for zircon, but is incredibly important. A lot of you guys mentioned monazite. This is the primary method that we use for dating monazite. So 232 at the top comes down to lead-208. The half-life here, 14 billion years, really, really long. So you have to have a lot of thorium in your system if you want to date anything precisely. Remove myself from temptation. Okay, so I'm not going to work through this in much detail today, but it's really important that any of you guys that are going into your qualifying exam, you want to know the decay equation, you want to know the age equation. Trust me, just work through it. The key thing here is that this is all based on this principle right here. The rate of change in the number of parent atoms is proportional to the number of atoms present. That is radioactive decay in a nutshell. And so the variables that we're working here with are time, right? That's what we want to know. That's what we want to solve for. The decay constant, we know this really well. We can throw uranium into a detector and we can figure out how quickly it's decaying. So we can get at kind of the decay constants. The number of parent atoms present at any given time, the number of parent atoms present at time 0, and then the number of daughter atoms present. And so what we end up doing is we end up getting to this equation down here where we have the daughter over the parent, this is actually what we measure, is equal to e to the lambda t minus 1. And again, we know this lambda pretty well, so we just need to solve for that to move it. I remove myself and I still try to go for it. Okay, so this is the example George uses every year, and I quite like it. So let's say you're at a bike race. You're gonna go race your bike in Portland, Oregon. That seems like a thing that people would do here. You show up to the race in the morning. Your mom is telling you, honey, don't go to the race. There's X probability of a crash today. If you know the number of riders, you know the number of crashes, you know the probability of a crash because your mom told you this morning, then you can actually calculate the duration of a race. So that's your time component. Okay, so the reason why uranium, thorium, lead is so powerful is because we have these three different clocks and they're all ticking at different rates. And so we can use them to answer different questions about different minerals through time. So what I'm showing here is time on the x-axis, going from the formation of Earth all the way to present day. And if we start off with our uranium-238 to lead-206 decay chain, we've only gone through one half-life, right? So one half-life later, hey, we're at 50%. So we went from 100% uranium-238 to 50%, from 0 lead-206 to 50%. Make sense? So we have something similar for uranium-235 to lead-207, but recall that the half-life is much, much shorter, so this is going to decay much, much more rapidly. So we get this really rapid drop-off in early Earth, where we have that early decay of uranium-235 and rapid increase in the amount of lead-207. And again, for that thorium-lead system, really long half-life, not great for dating a lot of processes that we're interested in unless you've got lots of thorium-232 in your system. Okay, so we're not really interested in the time, right? We're interested in the age. That's what we want to know as geochronologists. So we're going to switch these axes just slightly. So we now have age on the x-axis, the ratio of daughter, lead-206, to uranium-238 on the y-axis. And the way to think about this is if you took a crystal from, say, the Jack Hills, perhaps the most infamous zircon locality of them all, right, where we have crystals that are roughly at the age of the Earth, roughly 4.34 billion years old, and you took one of them and you measured its uranium-lead ratio, you would have equal parts lead-206 and uranium-238 because it's gone through essentially one half-life. So this means that this system, but in contrast, this uranium-235 to lead-207, we see again that really steep decline in early Earth's history. And so this makes this system really powerful for dating super old zircons, and this one more powerful for dating younger processes. We'll come back to that idea later if it doesn't quite sink in right now. And you guys should feel free to interrupt me or feel free to ask me questions after or during the break or whatever. Okay, so it turns out that we actually have kind of a bonus chronometer in this whole system. And this one isn't, it's not a decay chain, it's not like lead-206 does not decay to lead-207 or vice versa. But it's a function of how these processes work. So if we take our uranium-238 and lead-206 decay, and our uranium-235 and lead-207 decay, and we plug them into the decay equations that we saw a couple of slides ago, what we can do is we can divide the uranium, we can divide this equation by this equation. So we're just plopping blue on top of red, right? If we reshuffle those variables just slightly, we end up with this, uranium-238 over uranium-235. Now this is super powerful because this ratio, uranium-238 to uranium-235, turns out to be fixed in almost all rock types. This is one of George's magic numbers in geochronology, 137.82. And so we can just plug that number directly into this variable. And all of a sudden we have an extra chronometer system, right? Now we can deal with lead-206 to lead-207. So we can measure lead-206, we measure 207, we know half-lives, we don't really need to measure uranium-238 or 235 to get an age. We do anyway because we want it to confirm things on concordian space. And so this actually turns out to be a transcendental function, so we do need to iterate a bit to solve for the age, but it's completely feasible to do. Okay, so it turns out we're actually dealing with 4 chronometers. We just keep throwing more into the mix. So which ones are you guys going to use? Why, you can't report 4 ages on every single thing in your paper, right? You don't want to like list of 3,000 ages for every paper. Okay. So we're going to work through this by starting off with just this basic diagram here. So this is just showing some of the isotopes that might be present in any given mineral. So you're going to have uranium-238, uranium-235, thorium-232, and then their associated daughter products over here. We also get this guy, lead-204. Lead-204 is not a product of radioactive decay, but it's in your mineral when it crystallizes. It's in your mineral when it crystallizes, right? So it's living there. We know it's there. We measure it on our mass spec. So what do you guys think that means for 206, 207, and 208? Were they around when that mineral crystallized? Yeah, if we're getting some lead-204 in our system, which is not radiogenic, and we have some of it in our mineral, we're probably letting some of the other guys in too, right? So this isn't ideally what we would love is to have only uranium trapped in our crystal, no lead whatsoever, and all of that, everything that decays down is a product of radioactive decay. But that's not the case. We have this guy, initial lead. Make sense? Okay, so yeah, we've got just a bit of lead-206, lead-207, and lead-208 when this crystal is formed. So if you just go to your mass spec and you measure your uranium to lead ratios, and you've got extra lead in the system, what does that mean? Are your ages going to be too young or too old? Too old, right? Extra lead, a bit too old. That's not great. You don't want to do that. Okay. Any ideas on how we're going to work through this? This might be for the winners and learners. People have thought about this a bit more. We need some way to correct, to get rid of that lead-204, basically subtract it out of the system, and do the same for our 206, 207, and 208. Subtract out the common lead. What's this shiny mineral up here? Selena. Anyone know this composition? Lead sulfide. Lots of lead, right? We used to have a joke in grad school about, like, you know, if somebody was being mean to you, you're like, I'm going to bring the Selena to the lab. And we get really freaked out. Okay. So this is lead sulfide. And so what if we could go to lead sulfide deposits from the Archean, the Proterozoic, the Mesozoic, the Cenozoic, and measure their isotopic ratios of lead. So we're going to measure 204 to everything else. And then we can make a curve back through time, and we can use that curve. We're going to assume that basically that is, at that given time, that is the ratio of those leads to those leads. And we're going to use that to correct all of our zircon ages that we measure. So somebody really smart, two people really smart, did this in the 1970s. It's called the Spacey and Kramer's curve, 1975, or the classic paper. And so this is what we end up doing on all of our analyses. So we measure our 204, we measure our 206, 207, 208, and then we use these known ratios back through time to subtract out the appropriate amount of 206, 207, and 208. Okay, so we know that if we don't do this, we're going to get ages that are incorrect. But the question to you guys is, well, how much are they incorrect? Do you really care? Yeah, we care a lot, it turns out. So here's a way to visualize this. So on the y-axis, we're essentially looking at the ratio of radiogenic to common lead, and then the percent of age offset on the y-axis. So if you have young ages and have high common lead concentrations, then for the 206, 238 age, you maybe have a couple of percent offset on that age. This balloons on the 206, 207 age. So check this out. You know, if you're over here and you've got a billion-year-old grain and you've got whatever, a 6,4 factor of 200, you're all the way up here at 80%. We have to do common lead functions. Okay, so we're going to kind of forget this guy. I've mentioned this a few times. This isn't going to be particularly useful, the thorium-232 to lead-208 ratio. That's not going to be particularly useful for zircon. So we're going to turn back to those three chronometers that we've talked about a lot before. The uranium-238, lead-206, uranium-235, lead-207, and the lead-206, lead-207. And we're going to try to plot all three of these on the same diagram. So you guys have probably all seen a Concordia diagram at this point in your careers. And so the way that these things work is that we have lead-207 to uranium-235 on the x-axis, lead-206 to uranium-238 on the y-axis. And then we have this line here, which is called Concordia. And any place where these ages are the same will follow along this line. We know that lead-206 to uranium-238, the rate of change is nearly linear, right? Because of that really long half-life. We saw that in all of our diagrams. We've got this really sloped, curved shape to the uranium-235 to lead-207 decay chain. And so that's what's giving this strong curve to Concordia. Okay, so the way that this works in actuality, plotting things on it, is you have a crystal. It crystallizes in a magma, say times 0. A billion years later, it's going to be here. A billion years after that, it's going to be here. A billion years after that, it's going to be here. It's just going to move up Concordia through time. And so each one of these is connecting ages that are equal on the x and the y axis. Okay, so it turns out that we also managed to get our 6-7 ratio on here as well. And the way that this one works is a bit less intuitive, but it's not bad, I promise. So we're just going to take the slope of the line between our measured analysis, this concordant grain up here on Concordia, and the origin. What's the slope of the line? Rise over run. Everyone's taken math. So rise 206, 238 over run 207, 235. We rearrange this just slightly and we end up with what? Uranium 238 over uranium 235. We know that ratio, remember? 137.82. Plug that on in and we can solve for our H. Okay, so what are we actually going to measure on our mass spec to get to these ages? Turns out we don't need to measure all of these isotopes. So what most labs do is that they don't measure the 207-235 ratio. And the reason we don't do this is because it turns out that there's quite small abundances of uranium-235 in zircon. So instead, we're going to choose to measure the 206-207 ratio and the 206-238 ratio. Everyone fine with me so far? Okay, so you're probably asking yourself, okay, well, we're going to measure those two. Why don't we just plot those two on a diagram? So we do that sometimes. This is a different kind of diagram. We call this a Terra-Wasserberg diagram. We have uranium-238 to lead-206 on the x-axis, lead-207 to lead-206 on the y-axis, and you could calculate out your 206, 207 ages. Okay, but again, we talked about this idea that we don't want to go through a presentation to the manuscript, writing the first manuscript and be like, oh my God, I have to report 4 ages for every grain that I measured. So what are you actually going to report? This is critical, right? So the way that we do this is based on the precision of each individual age. And so the way that works is something like this. We have, for each individual analysis, we plot error ellipses. And these ellipses are basically showing the precision in all of the different ages. So if you look at an old grain, look at this huge uncertainty in 206, 238, huge spread on this axis. We also get a pretty large spread over here, but we get really precise on the 206, 207 axis, which is this kind of like line that goes down like this, right? For young grains, our error ellipses look much more like this. We get really precise 206, 238 ages. We don't do very well on the 207, 235. And then in this range here, oh, our ellipses are kind of wonky and we don't actually do a great job of measuring either very well. We've got a lot of imprecision there. Okay, so what are we going to use? This diagram is horrifying the first time you see it, but I promise it's not bad. So on the x-axis, we have age. On the y-axis, we have uncertainty in millions of years. And what you'll see is that for young, these blue colors are the 206, 238 age. These red colors are the 206, 207 age. For young grains, this 206, 238 age does much better. It's much lower uncertainty. At older ages, the opposite is true. The 206 to 207 age is much better. And then we've got this area, which just makes all geochronologists quite sad, where we don't really do super well on either. And so we're for young ages less than 1.4 billion, we're going to use the 206, 238. For old ages older than 1.4 billion, we're going to use the 206, 207. And we'll talk about this cluster a bit more in a few slides here. Okay, so we need to work through 3 complexities before we kind of move on to how we actually measure these things. So the first complexity is lead loss. The second complexity is inheritance. And then the third complexity is going to be overgrowth. So it turns out that in the crystal lattice of say zircon, uranium is bound into the lattice. It's nice and strong. It's in there. It's not going to move anywhere. Lead is not. And if you have, say, hydrothermal fluids coming through at 300, 400, 500 degrees C, flushing through your system, it's pretty likely that you're going to remove some lead. The result of that, this ends up looking something like this, where you begin to pull crystal off of Concordia down towards the origin.
So yeah, we have to leave in a bit. In like an hour or something.
Hey, Mark, can you mute yourself?
That's our lab manager, Mark. He's awesome. We'll meet Mark later. Okay, so we're going to go ahead and start pulling ourselves off of Concordia and down this line towards the origin. It turns out the amount that you get pulled off depends on grain size. So if you have smaller grains, they're going to get pulled more off of Concordia, right? You have a higher surface to volume ratio. You're going to be able to flush more lead out. It also depends on kind of the uranium concentration of those grains. So if you have higher uranium concentrations, you're actually going to lose a lot more lead because you probably have promoted metamorphization in the grain. You guys know that word? Yeah. Okay, so what happens if you now are a billion years later? Well, this Discordia line that we just formed here, right? We formed this Discordia line. All it's going to do is rotate up. It's going to remain completely straight. And there's a lot of power in this line. The upper intercept is going to give you the igneous age, the crystallization age of those zircons. The lower intercept is going to give you the hydrothermal age, when those fluids actually came through and flushed your system. 2 notes here. One is that we get a lot of users coming through our lab and they get really sad when they see this. And they say, oh, I just wanted concordant analyses. I wanted to know the age. You're getting 2 ages for the price of 1. This is super cool. This is really awesome stuff. So don't get discouraged if you see this. This is actually really powerful. The other thing to note is that many labs exclude discordant analyses. We're going to talk about this in a minute here. But oftentimes these analyses will not be reported in your data table. So if you're trying to make lead loss cords, make sure you go check in the full data table rather than the fully reduced data table. Okay. Okay, the second complication that we can have is inheritance, right? So in this case, we have a beautiful CL image here. We've got this beautiful zircon here, and then we've got this other zircon growing out around it essentially. We're going to talk more about these images in a bit. We're going to have our SEM lab manager talk about how these images are made. So So let's say we have a 2 billion year old country rock. We're crystallizing a new magmatic zircon. We often get these kind of mixing lines in between them. That's not too wild or unexpected. Just like before, we're going to see that they can move up Concordia through time. That line is going to remain straight. In this case, your upper intercept would give you the age of the country rock. The lower intercept would give you the igneous age. In space, this could look a lot like blood loss, right? CL images are a really good way to start parsing out which of those two variables you're dealing with. Okay, so we can also get complexities from overgrowth. It's quite common to get these metamorphic overgrowths. They'll often look like this in CL images where they're kind of these white ghostly overgrowths. And we get a similar pattern here where we have the same kind of mixing line between the upper intercept and the lower intercept. Something to keep in mind here is that high uranium thorium ratios are really indicative of metamorphic zircon. Low uranium thorium are indicative of igneous zircon. This is a really good kind of quick and dirty way to fingerprint your zircons because you're already going to be measuring those uranium and thorium ratios when you're getting your uranium lead ages. So this will come with any data set you collect anyway. This is kind of a cursory way to QC your data. Okay, so I brought up this issue of discordance and discordance filters, and this is critical, and this is, can't emphasize this enough. This is on the users to decide what discordance filters to use. When we reduce your data in a lab, we have to choose some discordance filter. We haven't chosen the right discordance filter for your data set. Only you can choose the right discordance filter for your data set. Okay, so the way that this works is well, you know, fine. If you're on Concordia, great. You know the age, you feel pretty comfortable with it. What if we have a detrital sample and it looks something like this, right? Well, is this grain, is this out here because of lead loss or inheritance? We don't really know. It's a really discordant, uncertain analysis. So we need to choose basically whether we're going to include all of these grains or whether we're going to cut out the most discordant ones over here and exclude them from our data set. Okay, so we can actually calculate that discordance. The way that we do that is by putting the 206, 238 age over the 206, 207 age, just like this, and you would get a percent concordance and a percent discordance. And once we've done this for all of our grains, we can calculate or we can choose a discordance filter. Basically, anything above 40% discordance is out of our data set. That would be a really high discordance filter. So here's how that might look like in actuality. So perhaps you guys have okay, so I worked a lot in Ecuador. Ecuador has a lot of really old terrains in it, and they've got a lot of discordant zircons because they've had a really prolonged history. Maybe you go with a loose filter there because you don't want to get rid of all of your old zircons, which are the more time it's around, the more likely it is to be discordant, right? It just has more probability to become discordant. So this, if you have old zircons, you might want to use a looser filter. A tighter filter, if you're trying to get a really tight analysis cluster, you're trying to get an MDA or something, maybe you want to go with a tighter filter, but realize that your age distribution is probably biased in this case. You're probably preferentially excluding older zircons. Again, this is the researcher's decision. Almost all labs are going to impose some discordance cutoff filter. At the end of the day, you guys need to go back in and make that decision for yourself and change it when appropriate. Yeah. Yeah, so for the tighter filter, you're only including the most concordant analyses. And so older ages, older grains have had more time to have lead loss or to inherit, whatever. And so they're usually, first of all, less precise, and two, they often have these complicated histories of them. Does that make sense? Cool. Okay. Okay, so what are you gonna do for discordant data? So this is actually the cutoff that we employ in our lab. So it looks a little bit different than what we saw before. Remember, we suggested this 1.4 GA cutoff age before. Turns out for discordant data, for things that aren't behaving so well, it's probably around 900 MN. So, you know, this again is a researcher decision. You're going to go into your data set, you're going to figure out where those ages transition over, and you're going to choose your discordance cutoff. Okay, so some best practices. We're going to include these at the end of each module. They're like just some text slides, but it's a good thing to like go through and remind yourself what you should be getting out of this. So you guys should all know at kind of a base level now how these ages are calculated. You're gonna understand why we use 206, 238, and 206, 207 ages. Hopefully you guys followed the background subtraction and how we're going to use a common lead correction using a curve-like spacing and framers. Hopefully you guys have a cursory understanding of Concordia diagrams and how we show 3 ages on the same plot, which is perhaps not the most intuitive thing. The relative precisions of these 2 chronometers, discordance and what can lead to it, right? So we've got inheritance, overgrowth, blood loss. And then I've put this red box around these 3 because I think this is kind of where the onus is on you guys now. So you got to use CL images to select your analyses and really understand what you're analyzing. You need to be in control of your discordance filter. That is absolutely on the user. And then figuring out where you want to set your cutoff ages between 206, 238, and lead 206, lead 207. Okay, so that's all I have for uranium lead basics. We'll do a lot more uranium lead stuff throughout the day, but I want to stop here and make sure we get any questions answered before we move on. We will talk a bit more about that on an applied data set, and we're more than happy to talk through. Yeah, we'll see if that answers your question later, and then we'll come back to it if it doesn't. Cool. Great.
As a question you mentioned, you can look at your choose to determine whether it's igneous or metamorphic. And I was wondering if you have a locality that you use for that, or if you
Yeah, so if it's over 10, then okay, sorry, for those of you online, the question was, is there a cutoff value for uranium thorium ratios for determining between igneous and metamorphic zircon? So typically people say that anything above 10 is probably metamorphic. It's not really that simple. There's a lot of petrogenetic ways that you can get uranium thorium ratios above 10 in igneous zircons. But that's kind of like if you're dealing with a detrital data set, you don't have another way to tell. That would be the first cutoff value. The last module of the day, we'll talk a little bit more about uranium thorium ratios, and it'll have some references on that slide that you can go check out for yourself if you're interested in that more. All right. Any other questions on this one? George, anything you want to add?
No, nothing has come in on the chat box. I think we're good with module number 1. Thanks for doing that.
Getting like this subtle wave of nickel sounding solid.